Hi, I'm Srividya. This project is about tools for algorithmic bias mitigation. Human decision making is prone to bias because of the societies we live in, the cultures we are brought up in, and the media we are exposed to. Algorithms were supposed to fix that, but surprise, they don't. They mitigate biases to some extent, but they also learn from the outcomes of human decision making. So a lot of that bias has seeped into machine intelligence. This and other algorithmic biases have led to poor decision making in many diverse fields. There are different types of algorithmic bias. They can be introduced at multiple points during the ML life cycle, and causes of bias may determine the best approach to manage it. So, bias detection and mitigation interventions can be implemented at each one of these points to control bias. Let's look at a simple use case of the UCI adult dataset where we predict the income class of a user. We use the AIF through 360 toolset to mitigate bias and use representative approaches across the ML life cycle. Now, deciding on fairness metrics was almost a project all by itself. The field of bias metric research is vast, and there are over 70 different metrics provided by AIF 360 alone. This cartoon here is a metric of how much my brain melted due to this problem. Now, realizing that there are two worldviews gives the problem structure. The first worldview is what you see is what you get. This assumes that whatever the data says constitutes an objective picture of the world, even if there are inequalities in the results. The second worldview is we are all equal. We are all equal assumes that data does not closely reflect reality due to biases that are inevitably contained within it. So different groups, differentiated by sex, gender, ethnicity, etc., should be similar overall, and we should mathematically compensate for any major discrepancies in the results. So, if we follow the WAE worldview, then we are most concerned about demographic parity. If we have the WYSIWYG worldview, then we are concerned about equalized odds. The proxy I'm using here is equal opportunity difference, which basically looks for equal true positive rates. We also want to look at predictive parity, and since this is an imbalanced data set, I will be tracking this as a difference of F1 scores in the unprivileged group and the privileged group. Note, the impossibility theorem states that only one of these three metrics can be optimized at the same time, which is also another reason I picked these three metrics. Now, do we have a problem? You know our use case. Post-experimentation, we are using the random forest classifier with no pre-processing, resampling, or any other method which might debias. The demographic difference of the original dataset is a whopping 20.01%. We want it to be as close to zero as possible. Post-prediction, we have an F1 score of 0.688. Demographic difference has actually gone up to 20.9%. The equal opportunity difference is 11.4%, and the accuracy difference is 7.9%. So, do we have a problem? Yes, we do. Now let's look at mitigation strategies in context to the ML lifecycle we looked at earlier. We can intervene at the pre-processing stage to modify the dataset to be more fair. Now, reweighing is a mild intervention. It only changes weights applied to training samples. It does not change any feature or label values. Disparate impact removal actually modifies the training dataset while maintaining its character and is a slightly more aggressive intervention. Next, we can do in-processing interventions which train a fair classifier. Adversarial debiasing tries to maximize class label prediction accuracy while minimizing predictability of the predicted attribute. Post-processing interventions let a model make predictions, then take these inputs in and recalibrate them to lower bias. I'll discuss the retiring adult dataset separately, but I'd like to draw your attention to the fact that it intervenes very early in the life cycle. Now let's look at the impact of these strategies. Now, as you can see here, the F1 score needs to be as close to 1 as possible, and our three parity metrics need to be as close to 0 as possible. As you can see, our demographic difference scores improve best with adversarial debiasing, but the lowering of the difference from 20.9% to 4.6% comes with a significant cost in accuracy as represented by the F1 score, which has dropped to its lowest at 0.49. Now, in the WAE worldview, this is fine because the ground truth is supposed to be different, is assumed to be different from the training data. Now, if you look at our other metrics, disparate impact removal has the lowest F1 score difference at 5.2% and the best improvement in equal opportunity parity with a difference of 8.5% as opposed to 11.4%. But the demographic parity is still really high at 19.4%. In the WYSIWYG worldview, however, this represents the ground truth. Now, this was tremendously unsatisfying because I still don't have an answer. Do we have a problem? Do we not? Is there a resolution? Now, bias can have some terrible impacts, but I submit that it is those impacts that we need to focus on. Algorithmic bias doesn't evolve the same way that human bias does, but it is an enabler of discrimination, which is the actual thing that we need to control. So I'd like to work on a utility-based metric for discrimination. This is some of the additional research I'd like to do. Thank you so much for listening.